In this video, I'm going to talking about instruction execution rate, that is average cycles per instruction, CPI. Another concept is MIPS rate, which is millions of instructions per second. Okay, clock speed is actually measured by cycles per second, which is hertz, or what we call the frequency, F. Frequency is expressed in hertz. Frequency F equal to cycles per second. To calculate the time interval of a known frequency is 1 over frequency. For example, 100 Hertz has a time interval of 1 over 100 Hertz, that is equal to 0.01 seconds. A processor is driven by a clock with a constant frequency f, or equivalent constant cycle time tau. Tau equal to 1 over f. Basically, when we're talking about the processor, we know we want to have the faster clock speed. For example, 1 gigahertz, 3 gigahertz. The frequency is hertz. That means within 1 second, they're going to have 1 billion cycles. This clock is controlled all instruction in the computer. In the chapter 2, introduced a concept is called cycle per instruction, CPI. What is exactly CPI? For example, a processor is driven by a clock with a constant frequency f, or equivalent constant cycle time tau. Tau is 1 over f. Instruction count, I, capital I, and smaller c, for a number of machine instructions run to completion or for some defined time interval. This number of the instruction is not the number of the line of the program. It's actually number of the machine instruction running in the CPU to complete one particular job. This instruction can be a loop, smaller set of the instruction running in the loop. And then we count total how many instructions actually execute in that time. Okay, here this I refer to the different type of the instruction, and then multiply the total number of the instruction count in that type, and then we can have the multiple times from I to 1 to number n, and then divided by the total number of the instruction count. And then this is the concept of the CPI, cycle per instruction. Okay, here gives the more detail for the type, how to define the type. Type is the different types of the instruction, such as load, store, branch, that is requires the different time, different clock cycle. For example, the Boolean logic operation is much faster than to load to access memory. So the different type of the instruction going to has different number of the clock cycle. So that is why I need to separate into the time. Furthermore, the total number of the time, the processor time need to be execute a given program equal to instruction count. Instruction count multiple the cycle per instruction, and each instruction how many cycles, and then how many total of the instruction multiple together, and then multiple the each cycle use how much of the time for that instruction, tau, and then multiple the tau, that is 1 over frequency, that is each cycle need how much of the time. Okay, all these three multiple together, we will get the total number of the time to run a given program. The further, we can also get into the more detail. For example, during the execution, part of the time to execute in the processor, which is more faster, and part of the time to transfer data from or to memory, the time of memory access is longer than the processor cycle time. Okay, here the definition is still same. I, capital I, is instruction count for the number of the machine instruction run to completion or for some defined time interval. Again, this number of the machine instruction is not the number of the code in the program. It's actually how many machine instructions to execute. It can be a loop for those several lines of the code repeatedly to run. So we count total how many instructions. To decode and to execute one instruction, multiple cycle of the clock. Okay, M is the number of the memory reference needed. How many times you want to reference memory? How many times you want to access memory to get memory data or write the data to the memory? The key is the ratio between memory cycle time and the processor cycle time. Memory cycle time is always longer than processor cycle time. Tau is a constant cycle time, so that is 1 over the frequency. Okay, so basically how many times of your memory access, and then multiply the key, that is the ratio of the memory time, processor time. This one is always bigger than 1. And then plus the number of the processor time to decode and execute. Okay, after they add together, and then we multiply the 1 over frequency, that is tau 1 cycle time, and then total how many instructions you have. So we get the total time. So this is basic concept of the CPI, and use the CPI can calculate the total time, and then here based on the different version, the memory access, processor access can calculate the total time. Okay. Another common measure of performance for a processor is the rate of instructions executed. Normally we use the million of the instruction per second, MIPS. Okay. How this millions instruction per second rate is calculated is basically the instruction count, how many total of the instruction, I, and instruction time, since it's a million of the instructions, so multiple the tens of the over 6 power. So this is total of the time t, and then 10 6 power. How this get it over here? So the t, we can use previous formula. The t is actually the total number of the instruction, and the CPI, cycle per instruction, multiply the tau, and then we use the millions, and then this is the total number instruction. Okay, and you see here had the total number instruction, here had the instruction. These two was canceled. So after cancel, the top is 1, and the bottom is has these 3. These 3 was left. Since we know 1 over f is tau, and 1 over tau is f. Okay, this one was actually represented by the frequency. So basically the final formula is the frequency divided by the cycle per instruction, and then the milling. Okay, this is millions instruction per second rate. The formula can be represented in this way. Okay, here is an example. Consider the execution of a program that results in the execution of 2 million instructions. Okay, this is 2 million instructions on a 400 MHz processor. So this is the frequency of the processor, and total number of the instruction is 2 million. The program consists of 4 major types of the instructions. The instruction mixed and the CPI for each instruction type are given below. So we're going to have a table. Based on the results of the program, trace the experiments. Here the table, that is the detailed data, instruction type, arithmetic, and logic. Instruction cycle per instruction is 1. Instruction missed 60% of this kind of instruction takes 60%. Logic computation is 60%. Load store with cache hit. So that is cache access. CPI is 2 cycles per instruction and is 80%. And branch is going to jump to the different section of the program. It's going to use the 4 cycle per instruction, and here has 12%. Memory access for the cache missing. If data does not in the cache, the data has to be loaded into the cache. That's going to use 8 CPI per instruction, and this is 10%. Okay, from here you already get an idea. The better you have big cache memory, so that you do not need to waiting for 8 instruction per cycle to waiting for the instruction. And also you want to eliminate the jump branch for your code. That's going to take more time. Load data, that is unavoidable, but the best way is use arithmetic logic calculation is only 1 cycle. Okay, this is add together is 100%. And let's see, the average PCI when the program is executed on a uniprocessor, this is one processor, with above trace result is CPI is 60%. This is a 60% plus 2 multiple 80% plus these 2 multiple 80% plus 4 multiple 12% and plus 8 multiple 10%. All this together is going to 2.24. That is, one instruction need to have average needs to have 2.24 cycles per instruction. The corresponding million instruction per second rate is frequency, and CPI multiple 8 to the power 6. The frequency is 400. We want to have millihertz, and then we want to multiply the 10^6 to the milli. And then divided by the CPI, we got the CPI 2.24, and then 10^6. And then this number divided by the number is going to be 178. Okay, this is the example in your textbook, example 2.2 on the page 51. Okay, that is for the CPI and millions instruction per second. Thank you very much. See you next time.